All right, howdy, and welcome to the final double lecture of the semester. So today I'm going to talk about diagonalization, eigenvectors and eigenvalues, and linear ODEs. So I'm going to start with a review. So, given an n by n matrix A, or I should say, and a vector x satisfying A times x is equal to lambda times x, where lambda is a real number. And we're also going to demand that x is not the zero vector. We say that lambda is an eigenvalue of A, and x is an eigenvector of A. So in order to find these kind of eigenvectors and eigenvalues, what we do is we let x be a variable, or actually I'm going to use something different. I'll actually stick with lambda. So let lambda be a variable. Then ax equals lambda times x is solvable for x not equal to 0 if and only if A minus lambda times the n by n identity matrix is singular. And of course, being singular is equivalent to the determinant of A minus lambda times in being equal to 0. So what we do is we define the characteristic polynomial p lambda of A is defined to be the determinant of A minus lambda times in. The eigenvalues of A are exactly the roots of p lambda. So, in order to find the eigenvalues of a given matrix, we write down its characteristic polynomial, and then we ask ourselves, where does this characteristic polynomial vanish? So, here is a proposition. And this is going to combine some of the things that we've said. So we're going to say let A be an n by n matrix and let lambda be a scalar, then the following statements are equivalent. So let me show that A implies B. Well, if lambda is an eigenvalue, then A minus lambda in times x has to be equal to 0 for the eigenvector, or for the associated eigenvector. And x has to be not equal to 0, so x has to be in the null space of A minus lambda times in. So in fact, I've shown not just A implies B, but I've also shown that A implies B implies C. And here, I guess I'm just using the observation from here that this is equivalent to this. And so now let me show that C implies D. So if the null space of A minus I times lambda is not equal to 0, then there exists x with A minus lambda in times x is equal to 0, which means A minus lambda in cannot be inverted. Because if it could be inverted, then I could multiply both sides of this equation by its inverse, and that would show that x is equal to 0, but we've assumed that x is not equal to 0. So that shows that C implies D. And finally, for D implies E, in fact, it's a bidirectional implication. We've already shown much earlier in the course that the determinant of a matrix is equal to 0 if and only if A minus I, or minus lambda times I is singular. So this is really a bunch of trivial statements that are kind of connected together by things we talked about earlier in this course. So let's recall the process then. We know how to find eigenvalues. We write down the characteristic polynomial and we find the roots. So once we know the roots, of P lambda, the eigenvector are precisely the elements of the null space of A minus lambda naught times in, where lambda naught is a root of P lambda. So the algorithm basically has two steps. First, you find the characteristic polynomial, then you find its roots, and then you analyze the null space of A minus a root times the identity matrix. And this is how you find all x and lambda satisfying this equation. So let's do an example. So say we run with the example A is equal to 2, 1, 1, 2. Then A minus lambda I2 is the same thing as 2 minus lambda, 1, 1, 2 minus lambda. The determinant of this is thus equal to 2 minus lambda squared minus 1, which is the same thing as lambda squared minus 4 lambda plus 3. Now, here's what we know. This right here is p lambda, and the roots of p lambda are given by the quadratic formula. You can also kind of guess them because they're not too hard to guess, but let's do it using the quadratic formula for the sake. So lambda naught is going to be equal to negative, and then we would have b, so negative 4, plus minus the square root of something, divided by 2a, a is 1, and then b squared, which is negative 4, so 16, minus 4ac, so minus 4 times 1 times 3. So this is the same thing as, there should be plus minus. 4 plus minus the square root of 4 divided by 2, which is the same thing as 2 plus minus 1. So lambda naught is equal to 1 or 3. And this is equivalent to saying that p lambda factors as x minus 1 times x minus 3. All right, so we have found its roots. Now let us kind of find the associated eigenvectors. So the next thing we do is we look at the eigenvector associated with lambda naught is equal to 1. Well then, a minus lambda naught times I2 is going to be precisely 2 minus 1, 1, 1, 2 minus 1, which is simply the matrix 1, 1. And you can check that the null space of this is going to be exactly the span of the vector 1, negative 1. So technically, since this is a span of a vector, it's actually the eigenvectors associated with this. So that completes the analysis of the eigenvector lambda naught is equal to 1. And now we can look at the eigenvectors associated with lambda naught is equal to 3, in which case we have a minus lambda naught times I2 is equal to 2 minus 3, 1, 1, 2 minus 3. So this is going to be negative 1, 1, 1, negative 1. And the null space of this, you can compute this again using row reduction if you so choose, is simply the span of the vector 1, 1. So this gives us eigenvectors for this eigenvalue and eigenvectors for this eigenvalue. So this is how we find eigenvectors and eigenvalues. Now, let's consider something interesting. So this time, I want to let A be equal to 2 here, and then negative 1 here, and then 1 here, and then 2 here. So very similar to the previous example, except now I have a negative sign here. But I want to go through the same process of find the eigenvectors and eigenvalues. Well, again, I look at the matrix A minus lambda times I2. So this is the matrix 2 minus lambda, negative 1, 1, 2 minus lambda. And then I look at the characteristic polynomial, which is going to be exactly the determinant of this. Which is going to be 2 minus lambda squared plus 1. And then I try to find the roots of p lambda. And again, I'm going to appeal to the quadratic formula. And so I'm going to get lambda naught is equal to, well, let's expand this out. If I expand it out, I get lambda squared minus 4 lambda plus 5. So here I'm going to get negative 4 plus minus the square root of negative 4 squared minus 4ac. In this case, a is 1, c is 5, so 4 times 5, all divided by 2. And so this ends up being the same thing as 4 divided by 2 plus minus the square root of negative 4. But notice there is a big problem. We have the square root of negative 4 here. So, if you recall, whenever you try to take the square root of a negative number, you run into problems. So, let's recall from algebra how we solve this. So, this will be an interlude. And so here's what the interlude is about. Let I denote the imaginary number I is equal to the square root of negative 1. Then every quadratic polynomial has roots of the form a plus bi for some a and b. So sometimes you can't find any real roots for your polynomial, but you can always find these roots. And these are called complex numbers, and they're called complex roots. So complex numbers come up naturally when you're trying to appeal to things like the quadratic formula. And we are going to make use of them in this course because they also come up when we're trying to solve these eigenvector, eigenvalue problems. So here's the upshot. If we allow ourselves to treat I like any other number, we can still solve our problem. But our eigenvectors and eigenvalues will involve complex numbers. Okay. So our approach to this is really just going to be to basically treat the imaginary number like any other number and then go about solving our problem. So this right here tells us that lambda naught is equal to 2 plus minus I, where I is the imaginary number. All right. So let's continue solving this problem. So let's try to find the eigenvector associated with lambda naught is equal to 2 plus I. Well, in this case, a minus lambda naught times I2 is going to be equal to, so I have a negative I here, a negative I here, a 1 here, a negative 1 here. And now I want to figure out the null space of this. So in order to do this, I'm going to do a row reduction, and I'm going to use the fact that I squared is equal to negative 1. So I have negative I, negative 1, 1, negative I. And what I'm going to do is I'm going to set row 1 equal to, actually I'm going to set row 2 equal to negative I, actually, sorry. I'm going to set row 2 equal to row 2 plus negative I times row 1. Why am I going to do this? Well, what is negative I times row 1? Well, this is precisely going to be negative I times negative I and negative 1 times negative I. So I can use the fact that I squared is equal to negative 1 to get the first entry here is negative 1. And the second entry is simply I. So when I add this to this, it cancels. And I get negative I, negative 1 for the first row, and 0, 0 for the second. Now, as we usually note, this corresponds to a bound variable. And this right here corresponds to a free variable. So we can translate to the linear system world, and we have negative I times x1 plus negative 1 times x2 is equal to 0. And we can express our bound variable in terms of our free variable. And this says that negative I x1 is equal to x2. If I multiply both sides of this equation by I, I'm going to get x1 is equal to I x2. And so now I have x1 determined by x2, which shows that the null space over here is equal to the span. So here I'm going to have 1 for x2, and here I'm going to have I for x1. And you guys can easily check that if you multiply this vector by this matrix, you get 0. So now I've identified the eigenvectors associated with this particular lambda. Note that they involve the imaginary number. Now let's do the same thing, except this time we're going to do the eigenvector associated with lambda naught is equal to 2 minus I. In which case, A minus lambda naught, I2, is going to be exactly I here, negative 1 here, 1 here, I here. And we want to figure out what the null space of this is. In order to figure out what the null space is, we're going to go through the same kind of row reduction calculation. So, how do we do this? Well, we have I, negative 1, and we have 1 I. What we're going to do is we're going to note that we can do the row operation of setting row 2 equal to row 2 plus I times row 1. Watch what happens if I take I and I multiply it by row 1. Well, I get I times I, which is negative 1. And then I get negative 1 times I, which is negative I. So if I add this row to this row, I get 0. So I'm going to get I, negative 1, and then 0, 0. Again, this is a bound variable. This is a free variable. And we have, translating to the linear system picture, x1 times I plus negative 1 times x2 is equal to 0. So this shows that I x1 is equal to x2. And now we're going to multiply both sides of this by negative I. If I do that, I'm going to get I times negative I, x1 is equal to negative I x2. Negative I times I just turns out to be 1. So I get x1 is equal to negative I x2. So I've expressed my bound variable in terms of my free variable. And that shows that this right here is equal to the span of the vector, you can take x2 to be 1, and then x1 has to be negative I. And you can check that this works. So, even though my matrix, when I looked at its characteristic polynomial, I did not have real eigenvalues, I had complex eigenvalues, I could still find eigenvectors associated with them. They just turned out to be eigenvectors with components that were imaginary too. So, here's the key point. If we use complex numbers, we can always find eigenvectors and eigenvalues of a given matrix. And this is based on something called the fundamental theorem of algebra. So, if P of x is equal to xn plus an minus 1 xn minus 1 plus blah 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 plus a naught, then P of x has n complex roots counted with multiplicity. So this is a very hard thing to prove, even though we call it the fundamental theorem of algebra. But it has a lot of applications. For example, if you consider the polynomial x squared plus 1, you can tell that this has no real roots because it's always greater than or equal to 1. But it does have complex roots, namely it factors as x minus I times x plus I. So even though this thing doesn't have real roots, it still has complex roots. In fact, 2 complex roots. And what the fundamental theorem of algebra says is that any polynomial of degree n always has n complex roots when you count them with multiplicity. And of course, some of these complex roots might be real, but the theorem doesn't exactly tell us which ones are real and which ones are complex. It merely tells us that it has a given number of complex roots. So this is important. And the reason it's important is that even if you are uncomfortable with imaginary numbers, imaginary numbers still show up in a lot of concrete applications, including ones to physics, including ones to solving differential equations. And right now I'm going to indicate why. And this is going to come back and be important later in the lecture. And it's not something I'm going to prove, but if you recall anything about power series from calculus, you can prove it yourself. So this is called Euler's formula. So let e be the exponential function, and I'm going to consider e to the a plus bi times x, where a and b are real numbers. Then you can show, basically by analyzing power series, that this right here is actually equal to cosine, e to the a times x times cosine of bx plus I times sine of bx. So it's a very, very beautiful relation relating the exponential function to the cosine and sine function. And I'm going to show you soon why this formula is so important for very, very concrete reasons. But we'll get to that in time. Before I do, I'd like to prove a theorem. So, let A and B be n by n matrices. If B is similar to A, then the two matrices have the same characteristic polynomial and consequently the same eigenvalues. So let me show you the proof of this. So what we're going to notice is that the determinant of A minus lambda times in is the same thing as the determinant actually, hold on, before I do this, let's note that because A and B are similar, we have that B is equal to S times A times S inverse. Now, we also have that the determinant of S times the determinant of S inverse is equal to 1. So this thing right here is actually the same thing as the determinant of S times the determinant of A minus lambda in times the determinant of S inverse. But we also know that the determinant of M times the determinant of N is the same thing as the determinant of M times N. So this right here is the same as the determinant of S times A minus lambda in times the determinant of S inverse, which itself is the same thing as the determinant of S times A minus lambda in times S inverse. And now we can distribute the S and the S inverse, and this is the same thing as the determinant of SA, S inverse, and then minus lambda SIN, S inverse. Now S times IN is just equal to S. So SIN times S inverse is equal to S times S inverse, which is equal to IN. So this thing is actually just the same thing as the determinant of S inverse minus lambda times IN. But we know that B is equal to SA times S inverse. So this is equal to the determinant of B minus lambda IN. So we can conclude with the observation that the characteristic polynomial of A, which by definition was the determinant of A minus lambda IN, is equal to the determinant of B minus lambda IN, which is equal to, is by definition the characteristic polynomial of B. So, since B was similar to A, we had this relation, and all these relations of determinants followed by taking advantage of this, and that established the equality of the characteristic polynomials. Because the characteristic polynomials are the same, they have the same set of roots, and thus the same set of eigenvalues. So that is one property of similar matrices. So let me state another fact. So suppose that the determinant of A minus lambda n is equal to lambda to the n plus c n minus 1, lambda n minus 1, plus blah, 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 plus c naught. Then c naught is equal to the determinant of A, which is equal to the product of the eigenvalues of A, and Cn minus 1 is equal to the trace of A, which is equal to the sum of the eigenvalues of A. So why is this true? Well, one way to think about this is basically to note that if we're looking at the determinant of this matrix, so A11 minus lambda, A22 minus lambda, blah, 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 blah. Actually, there's an easier way to prove this in a general case. It doesn't cover all cases, but it's kind of general. So I'm going to defer the proof for now. Defer proof until I talk about diagonalization. In which case I'll prove it for most matrices, if not all of them. And that will come later in this lecture. So it's just a general fact to know. It's not really used to prove anything, but it can be used like in various computational numeric things to kind of check the accuracy degree to which you computed your eigenvalues. So now let's do something else. Solving differential equations. Okay, so this is going to be our first real powerful application of eigenvectors and eigenvalues. But before I get into it, I want to do a warm-up. So for the warm-up, what I'm going to do is I'm going to consider the equation y prime of t is equal to alpha times y of t, where alpha is greater than 0. Well, one way to solve this, so the problem, by the way, is to solve for y. One way to solve this is to divide both sides by y of t. So we get y prime of t divided by y of t is equal to alpha. And then we integrate both sides, say from a to x, Now, the right side is very easy to evaluate. This will simply be alpha times x minus alpha times a, whereas the left side, we can do a u substitution. Our u substitution is going to be u is equal to y of t. So du is equal to y prime of t dt. And so this becomes the integral from a to y of x well, do I want to do a definite integral? Actually, it's somewhat easier to do this using indefinite integrals, so I'm going to do that instead. So if I do this using indefinite integrals, this is the same thing as alpha t plus some constant term c. And over here, by doing this u substitution, this ends up being the same thing as 1 over u du. And so this right here will evaluate to ln of u plus t is equal to this. So this shows that ln of yt is equal to alpha t plus e, where e is equal to c minus d. Now I can take this and I can basically hit it with an exponential function, and that shows me that y of t is equal to e to the big E times e to the alpha t, which is the same thing as some constant a times e to the alpha t. And so this right here is the general solution to the ODE. So maybe you've solved things like this in calculus before, but I just kind of want to warm it up and make it familiar again, because now we want to consider something harder. So in this example, we're going to have two differential equations. We're going to have y1 prime of t is equal to 3y1 of t plus 4y2 of t. And we're going to have y2 prime of t is equal to 3y1 of t plus 2y2 of t. So before we had a single equation to solve, but now we have two equations, and these equations are kind of intertangled. The derivative of y1 is expressed in terms of y1 and y2, and the derivative of y2 is expressed in terms of y1 and y2. Now, we can solve this ODE using eigenvectors and eigenvalues. So let me explain how this is done. First off, let's let boldface y be the vector consisting of y1 of t and y2 of t. And let's let A be the matrix 3, 4, 3, 2. Then this equation right here is equivalent to the equation y prime is equal to AY. All right. Now, we can solve this. We can find solutions of y prime equals AY by letting V be an eigenvector of V, or an eigenvector of A, and considering H of t equal to f of t, so this is a scalar, times the vector v. Then what we're going to do is we're going to note that this eigenvector is associated with eigenvalue lambda, so that if I plug this into this, what I get is h prime is equal to A times h of t, which is equal to f of t times A times v, but we know that v is an eigenvector of A with eigenvalue lambda, so this is the same thing as f of t equal to, or actually f of t times lambda times v. And over here, this is the same thing as f prime of t times lambda, or actually, I'm sorry, times v. So we get f prime of t is equal to lambda times f of t. And this is a single variable function, this f. It's a scalar. And so we can solve it exactly the way we solved it in the warm-up. And by the warm-up, we have that f of t is equal to A times the exponential of lambda times t. So one way to find solutions to this differential equation is to exhibit eigenvectors of A, find their associated eigenvalues, and then this times the eigenvector gives us a solution to this equation. So let's go back to our specific example. What we're going to do is we're going to consider A minus lambda times I2. This is the same thing as 3 minus lambda for 3, 2 minus lambda. And the determinant, which is p lambda, is equal to determinant of lambda A minus lambda I2, which is the same as 3 minus lambda times 2 minus lambda minus 12. And so if we simplify this, we're going to get lambda squared minus 5 lambda plus 6 minus 12. So this is lambda squared minus 5 lambda minus 6. and we can figure out its roots pretty easily. P lambda is going to be equal to, it's going to be lambda minus 6, and then times lambda plus 1. So the roots are 6 and negative 1. Let me sanity check myself for a minute. Yeah, okay, that's right. So now that I know the roots of this, I can go about finding the associated eigenvectors. So the eigenvector associated to lambda naught is equal to negative 1 corresponds, or the eigenvectors associated to lambda naught equals negative 1 corresponds to the null space of A minus lambda naught times I2. So we have to figure out what this null space is. Well, A minus lambda naught I2 is going to be equal to, let's see, I'm going to get a 4 here, a 3 here, a 4 here, a 3 here. So you can compute this null space, and if you compute it, you can see that the span of it is the span of the vector negative 1, 1. So what this shows is that HT is equal to A times e to the negative 1 times t times this vector right here, negative 1, 1, is a solution to y prime equals ay. So this solves this equation. For the case, for the eigenvector lambda naught equals negative 1, let's do another, or rather, let's do the other eigenvector. Or other eigenvalue. So the eigenvectors associated to lambda naught equals 6 correspond to things in the null space of A minus lambda naught I2, where A minus lambda naught I2 is equal to the matrix negative 3, 3, and then 4, and then negative 4. And so you can solve this if you want, but you can show that this is precisely the span of the vectors, or the span of the vector 4, 3. So from this calculation we did earlier, we know what f of t has to be. It has to be a times this, where the lambda is next to the argument in the exponential function, next to the t, So this shows that h of t, which is going to be equal to b times e to the 6 times t times the vector 4, 3 is a solution to y prime equals ay. So this completes the analysis of the solutions of this particular linear differential equation. And in fact, one can show that if you look at this solution right here and this solution right here, then they basically together span the solution space, and the solution space turns out to be a vector space. So I won't go into that. That's usually covered in more detail in an ODE course. Instead, I will do another example. This will be example 2. So suppose we have 2 tanks, tank A, and we have tank B. And what we're going to do is we're going to suppose that tank B has a pump leading into tank A. So the pump goes in this direction. And we're going to suppose that tank A has a pump going this direction. And so the rate here is going to be, say, liquid is going from tank B to tank A at a rate of 2 liters per minute. And then liquid is going from tank A to tank B at a rate of 3 liters per minute. And over here, I have 200 liters of water and 60 grams of salt. And over here, I have simply 200 liters of water. In fact, I'm going to make this nicer. So over here, this is going to be 2 liters as well. So the liquid that's going from here into here, well, there's also liquid going from here into here, and they're going at the same rate. So find functions y of t or how about this? Y a of t and y b of t, describing the amount of salt in tanks A and B at time t. All right, so let's think of what's happening. So we have 2 liters a minute of things transferring from tank B to tank A. So let's think about what's happening. If this is the amount of salt in tank A and this is the amount of salt in tank B, then these two are related to each other in the following manner. So this is going to be equal to plus 2 over, so 2 liters per minute over 200 liters of water. Or actually just say 200 liters in general. And then times the amount of salt in the tank B. And then minus well, things in tank A are leaving into tank B, so it's going to be, again, 2 liters per minute hold on. Let me fix one thing here. So if I do that, it's actually not going to be very interesting. Let me actually take the one from the book because it's solvable uniquely, and I think the one I wrote down was not solvable uniquely. Okay. So I'm going to actually take the one from the book because the one from the book is a little better because it has external inputs as well as the interconnectivity. So let's note that this starts with 200 liters of water. And 60 grams of salt. And over here, I just have 200 liters of water. Okay, so what we want to do is we want to determine the amount of salt in each tank at time t. So here's what we observe. YA and YB are related as follows. So YA is going to be or rather the rate at which the salt is changing is going to be 20 liters per minute divided by the size of tank A, which is 200 liters. So 200 liters. And then times the relative amount of salt. And so this is negative. And then it's going to be plus 5 liters per minute divided by 200 liters times the amount of salt we assume that's evenly mixed in tank B. So Y B of T. And likewise over here we have the rate of change of salt in tank B. Well, we have five liters is leaving per minute. Through here. So minus 0.5 liters per minute divided by 200 liters times YB of T. And then we also have the incoming ones from tank A. So this is plus 20 liters per minute divided by 200 liters times YA of T. But then we also have this flat 15 liters per minute is leaving. So in fact, if this is the amount that's leaving, it shouldn't just be -5, it should be -5 and then -15, so -20 total. Okay, now, unlike the equation I wrote down myself, this one is uniquely solvable. So this is the differential equation I want to solve, and I also have an initial condition. And my initial condition tells me that YA of 0 is 60 and YB of 0 is equal to 0. So now we're going to go about solving this system. So if I write down boldface y for the vector that has YA of t as the first component and YB of t as the second component, and I write down A for the matrix, which has entries, so -20 over 200 is the same as -1 over 10. 5 over 200 is the same as 1 over 20. actually, no. I'm being an idiot. That is 1 over 40. And then negative 20 over 200 here is, of course, the same as negative 1 over 10. And then the plus 20 over 200 here is the same as positive 1 over 10. So the system of equations we're interested in is precisely the vector equation. Y prime is equal to AY. But we also have an initial condition, which is that when I evaluate this vector at 0, I get 60 and 0. So this is the system we have to solve. And so we're going to solve this by finding eigenvectors of A. So how does this go? Well, what I have to do is I have to look at P of lambda, and this is going to be equal to the determinant of, let us note that this right here is the same thing as 1 over 40 times negative 4, 1, and 4. So this right here is the same thing as the determinant of this thing right here. Now, what I observe is that this determinant is going to be negative 1 over 10 minus x times 1 over 10 minus x plus 1 over 10 times 1 over 40 is going to be this. And so I want to find the roots. So the roots of P lambda are plus minus the square root of 3 over 20. All right, so that's very nice for us. Now, what we can do is we can consider our problem. So let's see. So why did I get a slightly different answer than the book? Let me stare at this for 1 second. Oh, I see. Okay. So right here, you see how I have B here and A here? I accidentally reversed the order. That means I should have had this switched. Okay, so sorry, I had a mistake here. This should have been negative 1 over 10. This should have been positive 1 over 10. Let's erase all this. Let's correct this. Move the negative sign. And then, now, the roots of this just to sanity check myself. Are negative 3 over 10 and 1 over 20. All right. So now what we would need to do is we would need to find the null space of A minus, say, negative 3 over 20 times I2. Now, this would be a kind of annoying row reduction calculation, so let's just see what the answer is. Well, the answer is, it is the span of the vector 1 and negative 2. And likewise, we would need to check what the null space of A minus negative 1 over 20 is, times I2. Again, another annoying row reduction calculation, but in the end, you get that this is the span of 1 and 2. So, we find the following general solution. To y prime is equal to ay, and this general solution is going to be given by h of t equals c naught, and then times e to the negative 3 over 20 times t, and then multiplied by this vector right here, 1, negative 2, and then plus c1 times e to the negative 1 over 20 times this vector, 1, 2. So this is wonderful. But what we need also is we need not just the general solution, we need that h of 0 is equal to 60 and 0. So let's note here that abstractly, if we evaluate this at 0, we get c naught times the vector 1, negative 2 plus c1 times the vector 1, positive 2, which is the same as c naught plus c1 in the first component, negative 2 c naught plus c1 times 2 in the second component. And so what we're demanding is we're demanding c naught plus c1 is equal to 60, and negative 2 c naught plus 2 c1 is equal to 0. Now, in order to solve this, you could basically use any of the techniques at the start of this course, or you could simply see that taking c naught to be 30 and c1 to be 30 instantly solves this equation. So c naught equals 30, c1 equals 30, gives us a solution. And so, we find that h of t is equal to 30 times e to the negative 3 over 20 times the vector 1, negative 2 plus 30 times e to the negative 1 over 20 times t times the vector 1 over 2 is the solution. which means ya of t is equal to 30 e to the negative 3 over 20 times t plus 30 times e to the negative 1 over 20 times t, and yb of t is equal to negative 60 e to the negative 3 over 20 times t plus 60 times e to the negative 1 over 20 times t. And so finally, we have solved our system of equations. So this is another example indicating how eigenvectors and eigenvalues can be used to solve differential equations. Let us do one final one. So now, this will be example 3 for ODEs. What we're going to do is we're going to consider the equation y prime is equal to ay, where A is the matrix 1, 1, negative 2, and 3. And we're going to try to solve this. We're going to try to find the solution. H of t with h of 0 equal to 1, 1. So our strategy is going to be generally the same, which is first we try to find the eigenvectors and eigenvalues of A. So we write down the characteristic polynomial. Now, let's work it out, what the characteristic polynomial has to be. So I get lambda squared minus 4 lambda, and then plus 5. Now, the roots of p lambda can be figured out by the quadratic formula. So this is going to be equal to plus minus negative 4. Actually, I'm sorry. Minus negative 4 plus minus the square root of negative 4 squared minus 4ac, so 4 times 20, or 4 times 5, all divided by 2. And so this will simplify to 4 plus minus 2 times the imaginary number divided by 2, which again simplifies to 2 plus minus the imaginary number. So we have found the roots of p lambda, and we can see that they involve the complex numbers. So let's try to continue the solving process. The eigenvectors associated with lambda naught equals 2 plus I correspond to things in the null space of A minus lambda naught times I2, which is the same as the null space of Well, I'm subtracting 2 plus I from 1, so negative 1 minus I, and then 1 minus I here, 1 and negative 2 here. And you can compute this null space. I'm not going to do it for you, but this null space precisely turns out to be the span of the vector. You can have a 1 here and a 1 plus I here. And again, you would compute this basically by doing the same ordinary operations associated with row reduction. Likewise, we can compute the eigenvectors associated with lambda naught is equal to 2 minus I. Well, in this case, we're looking at the null space of A minus lambda naught times I2. This will be equal to the null space of, so I have to subtract this lambda naught from 1 and from 3. So I would get negative 1 plus I and 1 plus I. And here I would keep my 1 and my negative 2. And again, you can very easily compute the null space here to be the span of this vector. I guess I should tell you guys what trick I'm using at this point to very quickly compute the null space. Every 2 by 2 singular matrix is of the form A, B, and then K, A, K, B for some K. And here's what we know. If we set B here to be the first component and negative A to be the second component, you can check that when you multiply this vector by this, you get 0. So in fact, it's very easy to figure out what the kernel of a 2 by 2 singular matrix is. All you do is you reverse the order of these, and you give the bottom one a negative sign. So that's the same trick I was applying in both of these situations to figure out what the span is. Generally speaking, you'd want to figure out what the null space is using the row reduction algorithms that we talked about, but this is kind of a cheap little trick that lets you do it quickly when you're crunching for time. But it's only a trick that works for 2 by 2 matrices. So here's what we now have. We have two special solutions. The solution corresponding to lambda naught equals 2 plus I is h of t equals A, actually I'm going to use a different letter, so I'll say C naught, for example. C naught times E to the 2 plus I times T times the vector 1 and then 1 plus I. Now, this is hard to think about because we have a lot of imaginary numbers and it's hard to kind of think about this as a function. but we can recall Euler's formula. And what Euler's formula taught us is that e to the 2 plus I times t is the same thing as e to the 2t times cosine of t plus I times sine of t. So this is actually equal to C naught cosine of t plus I times sine of t all times e to the 2t times 1 in the first component and then 1 plus I in the second component. And this simplifies. So let's see how it simplifies. Well, I can write it as the sum of two vectors, one real and one imaginary. So in the real vector, I'm going to have C naught times cosine of t times e to the 2t. I'm also going to have C naught times cosine of t e to the 2t. And then I note that when I multiply I sine t times this I right here, I'm going to get minus, actually let me manipulate this a little bit. I can pull out various things. I can pull out the C naught and I can pull out the E2t. So I can pull out the C naught and the E2t. I can do that over here as well. And so here I'm going to have cosine of t. And down here I'm going to have cosine of t. And then minus sine of t. Over here, for the imaginary part, well, for my first component up here, I'm going to have the I times sine of t, so I'll have a sine of t here. And then down here, I can see that I get an I times a cosine. So I'm going to have a cosine of t here. And then I can also see I get a 1 times I plus sine of t. So I get plus sine of t. Now, I have these two interesting vectors. This vector and this vector. And now here's the awesome fact. Let's set h naught to be the real component. So it's going to be this first thing. So C naught e to the 2t and then times cosine of t and then cosine of t minus sine of t. And we're going to set h1 of t to be the other thing. So, and I'm going to change my constant term here, by the way. So I'm going to call this C1 now. E1, C1 times e to the 2t times sine of t, and then cosine of t plus sine of t. Then h naught and h1 together form the general solution to the ODE. So what we can do is we can go back to trying to solve the problem that we were originally interested in. Which is, we wanted to find a solution to this system satisfying this equation. So we're interested in basically finding an h of t satisfying y prime is equal to a y, but we also wanted to satisfy h of 0 is equal to 1, 1. Well, this right here is going to be, for us, the sum of these two functions. So c naught e2t cosine of t, cosine of t minus sine of t, and then plus c1 e2t sine of t cosine of t plus sine of t. Well, if I set this equal to 0, then I get h of 0 is equal to c naught. E to the 2 times 0 is just 1, so this becomes 1, because cosine of 0 is 1, and then 1 minus 0, plus c1 times 0, 1 plus 0, which means this is the same thing as c naught here, and then c naught plus c1 here, which shows that if this is equal to 1, 1, then we have c naught is equal to 1, and we have c1 is equal to 0. So our desired solution is simply e to the 2t times cosine of t, and then cosine of t minus sine of t. So if you think about what we did, it's kind of amazing. And I want to go through it one more time. We are trying to solve this differential equation where we have this matrix A, and y here is the vector with entries y1 of t, y2 of t. And we want to find a solution satisfying this property. So this is called an initial condition. Well, we go about trying to find the eigenvectors of A, and we find that the eigenvalues are imaginary, and the eigenvectors themselves also have imaginary components. And we're like, okay, we can tolerate that. You know, we're just going to try to go through the rest of the problem and solve it. So we find the eigenvectors, and then we use these eigenvectors to write down solutions. So in this case, we write down the solution h of t is equal to c naught times e to the eigenvalue times t times the corresponding eigenvector. We know that this is a solution, just in accordance with the general principle that we established earlier in the warm-up. And then we say, okay, let's expand the solution in terms of its real component and its imaginary component. And the thing is, both the real component and the imaginary component have to be solutions in their own right. So we get from this two separate solutions, one corresponding to the real, one corresponding to the imaginary. And we wrote them down here. And here I stated a fact, which I didn't prove. And this is kind of beyond the scope of this course. You can prove it in an ODE course or consult an ODE textbook if you're really interested in it. But we were able to extract from the real component and the imaginary component two solutions. we use the fact that these solutions form the general solution to the ODE, and then we looked at their sum, and we tried to choose C0 and C1 such that H0 satisfied the initial condition. We found that C0 has to be 1 and C1 has to be 0. And that finally gave us our desired solution. So that completes the proof of, or at least the computation of the solutions of this differential equation. So I hope this all indicates how eigenvectors and eigenvalues can be used to solve ODEs. Next, I want to do some general theory. And so I'm moving on to diagonalization stuff. So we want to consider the following statement. Theorem: if lambda 1, lambda 2 through lambda k are distinct eigenvalues of an n by n matrix A with corresponding eigenvectors x1 through xk, then x1 through xk are linearly independent. So let me prove this real quick. Suppose x1 through xr is the smallest is chosen with the smallest r such that x1 through xr is linearly dependent. So we're gonna assume that this is possible, that we can find such an r such that these vectors are linearly dependent, and we're going to choose the smallest such r. So we have a linear relation c1 x1 plus c2 x2 plus blah 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 cr xr. And now what I'm going to do is I'm going to apply my matrix A to this. So if I apply A to this, then A c1x1 plus A c2x2 plus blah 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 cr xr is the same thing as c1 A x1 plus c2 A x2 plus blah 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 cr A xr. Oh, by the way, this is equal to 0 because it's a linear dependence relation. So if I apply A to this, I get this, which is also equal to this. So basically I'm noting that since x1 is an eigenvalue with eigenvalue lambda 1, I can replace this with lambda 1 times x1. Likewise, I can replace this with lambda 2 times x2 plus blah 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 cr lambda r times xr. And this of course is equal to 0. So I know that this is equal to 0, and I know that this is equal to 0. And what I'm going to do is I'm going to multiply this relation here by lambda r. So I'm going to get c1 lambda 1, or actually, yeah, c1 lambda r x1 plus c2 lambda r x2 plus blah 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 cr lambda r xr. This is equal to 0. And so now I have these two relations. And what I can do is I can subtract them. If I subtract them, oh, okay, it didn't freeze. That's good. If I subtract them, then what I get is I get c1 lambda 1 minus lambda r times xr, or times x1, plus C2 lambda 2 minus lambda r times x2 plus blah 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 CR minus 1 lambda r minus 1 minus lambda r times xr is equal to 0. Now, not all of these coefficients are 0. In particular, these things right here are never equal to 0. The reason they're never equal to 0 is because we've assumed that these vectors, x1 through xk, have distinct eigenvalues. So since not all of these coefficients are 0, it follows that x1, x2, all the way through xr minus 1 is linearly dependent. And this right here is a contradiction. The reason it's a contradiction is because we assumed r here was chosen to be the smallest r such that x1 through xr is linearly dependent. But our argument just showed that in fact x1 through xr minus 1 also has to be linearly independent. So consequently, there is no r such that x1 through xr is linearly dependent. And that completes the proof, because in particular it shows that x1 through xk have to be linearly dependent. Now, time for the fundamental definition. We say that an n by n matrix A is diagonalizable if there exists a non-singular matrix X and a diagonal matrix D such that X inverse times A times X is equal to D, and we say that X diagonalizes A. So, what this essentially does is this says A is similar to a diagonal matrix. And our diagonal matrix D might look something like this: lambda 1, lambda 2, blah, 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 lambda n. And diagonal matrices are really, really nice because, you know, if you take the diagonal matrix D and you multiply it by the vector x1, x2 through xn, well, you simply get lambda 1 x1, lambda 2 x2, blah, 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 lambda n xn. So it simply scales the components by the corresponding values. So the geometry of a diagonal matrix is much easier to understand in terms of what it's doing to a vector than an arbitrary matrix A. So if our matrix is diagonalizable, we can, after doing a similarity transformation, make it into something we can very easily understand. So this is equivalent to saying there is a basis for Rn in which A acts as a diagonal matrix. Okay? So now we want to kind of try to understand what the relationship is between diagonalizable things and eigenvectors and eigenvalues. And this is given by the following major theorem. We say that an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So I'm going to prove one direction of this, which is namely, I'm going to get rid of this, and I'm going to assume that n has n linearly independent eigenvectors. And the other half of the proof, you can read it in the book if you're curious. So, suppose A has n linearly independent eigenvectors. x1 through xn. And we're going to call this set E. Then A times x1 is equal to lambda x1. A times x2 is equal to lambda 2 x2. Blah, blah, blah. A xn is equal to lambda n xn. So, with respect to the basis E, A acts as a diagonal matrix. So let's consider the following diagram. We have Rn with the standard basis, and we have our matrix A. And then we have our basis E, which we've just talked about. And so we can talk about coordinate vectors with respect to the basis E. And from this computation right here, we see that A acts as a diagonal matrix with respect to this basis. So it acts by D equals lambda 1, lambda 2, blah, 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 lambda n. And we also have change of basis matrices. X going from coordinate vectors in E to the coordinate vectors corresponding to the standard basis. And X is the matrix with components. First column is x1, second column is x2, blah, blah, blah. Final column is xn. So we have the following relation between D and A, which is D is the same thing as first you go up by x and then over by A, and then you go down by x, that corresponds to x inverse. So this shows that A, or D is equal to this, and A is equal to this. So this right here basically shows that the matrix A is similar to the diagonal matrix D. And all I needed for this to be true was I needed that A had n linearly independent eigenvectors. And now I'm just going to state a general fact. Almost every. So note the word almost. This is the key thing. Almost every matrix A is diagonalizable. I'm not going to go into the matrices that are not diagonalizable. Basically, you need to bring in other techniques, particularly this notion of a Jordan normal form, and it's not something that we cover in this course. I don't even think it's in the textbook. It's certainly not in chapter 6. But you can say something that's true for every matrix, but you cannot say that every matrix is not diagonalizable. So I guess I'll say this very explicitly. However, there exists non-diagonalizable matrices. Let me give you an example of something that's not diagonalizable. Suppose we take A to be the matrix 1, 1, 0. Actually, 1, 1, 0, 1. Then the determinant of A minus lambda I2 is easily checked to be 1 minus lambda squared, and this has exactly the root lambda. So this is p lambda, and the only root of p lambda is 1. So now let's try to compute the null space of A minus 1 times I2. Well, this is the same thing as the null space of the matrix 0, 1, 0, 0. And the null space of this is easily checked to be the span of the vectors 1, 0. So this matrix has only one eigenvalue and only one eigenvector associated with that eigenvalue. So since, if we look at the statement of this theorem, this matrix does not have two linearly independent eigenvectors, which means it's not diagonalizable. And this is using the direction of the theorem that I did not prove. So this is just to kind of indicate that certain things can go wrong, but I don't really want to focus too much on that in this course. Instead, I'm going to look at examples where things actually do go right. So let's do an example. So example 1, diagonalize the matrix. A is equal to 2, negative 3, 2, negative 5. So again, first thing I have to do is I have to write down the characteristic polynomial, which is defined to be the determinant of the matrix 2 minus lambda, negative 3, 2, negative 5 minus lambda. This is, of course, 2 minus lambda times negative 5 minus lambda plus 6. So I'm going to use Wolfram alpha to help me out here, just to save a little bit of time. 2 minus x, negative 5 minus x plus 6. And the roots are negative 4 and 1. So roots are lambda equals 1, lambda naught equals negative 4. So now we can look at the eigenvector, or the eigenvectors, associated with lambda naught is equal to 1. This corresponds to the null space of 2 minus 1, negative 3, 2, negative 5 minus 1, which is the same as the null space of 1, 2, negative 3, negative 6. Which, again, we can easily compute using our favorite little trick. And we see that this is exactly the span of the vector 3, 1. And likewise, we can go over here and we can compute the eigenvectors. Associated with lambda naught equals negative 4, correspond to things in the null space of 2 minus negative 4, negative 3, 2, negative 5 minus negative 4, which is the same thing as the null space of the matrix 6, 2, and then negative 3, negative 1. And again, we'll use our little trick that I talked about earlier to see that this is precisely the span of 1, 2. So we found 2 eigenvectors, and we note that their spans, the span of this forms all eigenvectors associated with 1. The span of this forms all eigenvectors associated with negative 4. So now set E to be equal to the basis 2, 1, and actually 3, 1, and 1, 2. Then we can write down our diagram from earlier. With respect to this basis, A is given by the diagonal matrix D is equal to 1, negative 4, and 0, 0. And then with respect to the standard basis, it's given by the matrix A, so 2, negative 3, and then 2, negative 5. And then we also have the base change maps. This is X, and it's given by the matrix, so 3, 1, 1, 2. Now, let's quickly note that x inverse here is going to be 1 over 5 times, let's see, 2, -1, -1, 3. Let me sanity check myself for a second. Yeah, so this is the inverse of x. So it follows that d is equal to if this is A, then d is equal to x, A, x inverse. So 1, 0, 0, -4 is equal to 1 over 5, 2, -1, -1, 3, times 2, 2, -3, -5, times 3, 1, 1, 2. And this precisely diagonalizes our matrix. So this completes the diagonalization of the matrix A. Let's do another example. So, for example 2, I'm going to look at the matrix 3, 2, 2, -1, 0, -1, -2, -2, and then -1. And what I want to do is I want to diagonalize A. So first things first, I have to find the eigenvalues of this. So to find the eigenvalues, I have to compute P of A, which is going to be the determinant of 3 minus lambda, 2, 2, -1, 0, -1, and then -2, -2, -1. Oh, I should have a negative lambda here, a negative lambda here. So, let's note that this is the same thing as 3 minus lambda times negative lambda times -1 minus lambda minus 2, and then minus 2, and then -1 times -1 minus lambda minus 2, and then plus 2, -1 times -2. By the way, I'm just doing a cofactor expansion here. Minus -2 times negative lambda. So I want to find the roots of this. So the roots of P lambda. So to do this, I'm going to cheat and use Wolfram alpha, because otherwise I'm in for a long, tedious computation. So 3 minus x, -x, -1 minus x minus 2, minus 2, -1, -1 minus x, minus 2, plus 2, 2 minus 2x. And so the roots are 0 and 1. All right, so now we're going to analyze the roots. So first thing I'm going to do is look for eigenvectors associated with lambda naught is equal to 0. So this corresponds to finding the null space of the matrix 3, 2, 2, negative 1, 0, negative 1, negative 2, negative 2, negative 1. So again, I could solve this by using row reduction, but I am kind of lazy. So instead, I'm just going to note that this is the first two rows here are linearly independent. So, or the first two columns are linearly independent. And since the column space plus the null space is equal to 3, we deduce that the null space has to be 1. And you can quickly check that the vector 1, 1, 1 is in the null space. So it's very easy to compute the null space associated with 0, which is the span of 1, 1, 1. And I can also find the eigenvectors associated with lambda naught is equal to 1. I'll probably have to work a little bit more for this one. So this is going to be the null space of the matrix 3 minus 1, 0 minus 1, negative 1 minus 1, and I transcribe everything else. And so this is precisely the null space of the matrix 2, 2, 2, negative 1, negative 1, negative 1, negative 2, negative 2, negative 2. Note that this vector and this vector, these column vectors, are both multiples of the first column vector. So you can check that the column space of this matrix has dimension 1, which means the null space has to have dimension 2. And it's very easy to check, or it's very easy to find two vectors in the null space. I'm just going to exhibit them. So for example, 1, 2, 0 is in the null space. And you can check that by just multiplying this vector by this matrix, or by actually computing the null space using row reduction. And you can also check that 1, 0, 1 is an element of the null space. So I now have my eigenvectors and my eigenvalues. So what I do at this point is I set E to be the basis 1, 1, 1, 1, 2, 0, and 1, 0, 1. I note that this first one is associated with the eigenvector 0, whereas this and this are associated with the eigenvector 1. And I write down my base change diagram. So I have R2 here with the standard basis, R3 with the standard basis. And I have a map between the R3s given by A. And then I can look at R3 with the E basis, coordinate vectors. And again, coordinate vectors with respect to the E basis. And with respect to the E basis, I know what A does to these vectors. It multiplies this vector by 0, it multiplies this vector by 1, this vector by 1. So it's given with respect to the E basis by the diagonal matrix 0, 1, 1. And then I also have the base change maps, where the base change maps are given by x is equal to the matrix 1, 1, 1, 1, 2, 0, and 1, 0, 1. And it follows from this diagram that D is equal to A, or X, A, X inverse. And I'm going to omit the calculation of X inverse because it's just the inverse of a 3 by 3 matrix. And we've done plenty of those in this course. So this shows that A is similar to the matrix 0, 1, 1. And hence is diagonalizable. All right. So now I'm going to finish with a proof of something I mentioned at the start of today, which is that, let me actually go back and grab it. So I claimed that Cn minus 1 here and C naught have the following interpretations. C naught is the product of the eigenvalues, and Cn minus 1 is the sum of the eigenvalues. And I told you guys that I would defer the proof until I discuss diagonalization. Well, I've discussed diagonalization, so now let me say how this is proved. So, suppose A is diagonalizable. That is, B, A, B inverse is equal to D, which is equal to lambda 1 times lambda n. And we know that if it's diagonalizable, then these are the eigenvalues of A. So let's consider the characteristic polynomial, P lambda. This is defined to be the determinant of A minus lambda in. But this is the same thing as the determinant of B times the determinant of A minus lambda in times the determinant of B inverse. Basically, I'm using the fact that this times this is 1. And this is the same thing as the determinant of B, A minus lambda times in times the determinant of B inverse, which is the same thing as the determinant of B, A minus lambda in, B inverse, which is the same thing as the determinant of B, A, B inverse minus lambda in, which is the same as the determinant of D minus lambda in. But now we can interpret this. The determinant of D minus lambda in is the same thing as the determinant of delta 1, or lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda, which is equal to lambda 1 minus lambda times blah, 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 lambda 2 minus lambda, blah, 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 lambda n minus lambda, So if you expand this out simply by using the distributive law, you get that this is the same as lambda n times -1 to the n plus -1 to the n minus 1 times the sum of the lambda I from I equals 1 to n times lambda to the n minus 1, and then plus blah, 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 -1 to the 0 times lambda 1 times lambda n. And so this right here is C naught, and this right here is C n minus 1. And so I guess I have to correct my term slightly. C n minus 1 is actually equal to -1 to the n minus 1 times the trace of A. So this completes the proof of the statement I mentioned at the beginning of class, and it's simply a consequence of diagonalization. The main point of diagonalization is to take an arbitrary matrix A and then, using its eigenvectors and eigenvalues, put it in a diagonal form where its geometry is most cleanly understood. So that is all I have for you for today, and this covers basically all the material that can and will show up on the final exam. So I will do a two-part review session, one during class time on Friday, and then another on Saturday evening from 6 to 10. So I hope to see you all then, and I'll also be posting a homework along with this stream.